This video is on finding a basis for the null space of a matrix. I'll be talking about it for a bit, then doing examples. If you'd like to skip to the examples, I have links in the description to where each example begins. The examples I'm doing are finding the null space of a 2x2, 3x3, a 3x3 in which the dimensions of the basis for the null space is 2, and a 2x3 matrix. A basis for the null space is a set of vectors that represent all vectors that will result in the zero vector when multiplied by some specific matrix. That is, any linear combination of vectors in the basis for the null space will create a vector that when multiplied by the matrix of interest will result in the zero vector. The dimension of the basis for the null space is decided by the number of free variables, which is decided by the number of non-pivot columns in that row-reduced matrix. To have vectors besides just the zero vector in any matrix's null space, the matrix must be dependent. When a matrix is independent, its columns are all independent and unrelated by any linear combination of each other, meaning it's impossible to find some combination of them that will result in the zero vector. The only linear combination that will do this is multiplying each column by 0, then adding them, which is the same as multiplying that matrix by the zero vector, making the zero vector the only one present in the null space for that matrix. If a matrix is dependent, at least one column is a linear combination of one or more columns. This means that there are more vectors besides just the zero vector that can be multiplied by this matrix to result in the zero vector. For a 2x2 dependent matrix, the second column will be a multiple of the first, or vice versa. This matrix is pretty obviously dependent, but if you can't tell, you can always take the determinant to check. Now that you know it's dependent, you know there's a vector other than just the zero vector that makes up this matrix's null space. Next, row reduce. I do this by multiplying the top row by 2 and subtracting the second row and sending that to the second row. Now that it's fully reduced, you set up some vector next to it and set it equal to the zero vector. As you can see, there's a non-pivot column in the second column. This indicates a free variable in the second component of the null space vector. Set the free variable to 1. Next, think what first component would result in a 0 once multiplied by 1 and added to 3. If you don't want to do this by inspection, you can set up a simple algebra problem. x1 times 1 plus 3 times 1 equals 0. Solve for x1 and get negative 3. Negative 3, 1 is the basis for the null space of this matrix. This means any multiple of this vector will result in the zero vector once multiplied on the right to this matrix. In this example, it's not clear that the matrix is dependent, so you can take its determinant to check that it's 0. Now you can start row reducing. I start by making my matrix upper triangular. I do this by first adding row 1 to row 2 and sending that to row 2. Next, I take negative 2 times row 1 plus row 3 sent to row 3. Then I add row 2 to row 3 and send that to row 3. It is clear at this point that there isn't any other way to reduce this matrix. I multiplied each row by negative 1 just to make things positive. Next, you set it up being multiplied by some vector and set equal to 0. Since there's a non-pivot column in the third column, the third component of the null space vector is a free variable and is set to 1. The second component is found by thinking of what would need to be multiplied to 15, so it adds to 6 to result in 0. You can also set up a simple algebra problem. 0 times x1 plus 15 times x2 plus 6 equals 0. Solve for x2 and get negative 6 over 15, which reduces to negative 2/5. To find the first component of the null space vector, you can set up a simple algebra equation and solve for x1. You have 2 times x1 plus 9 times negative 2/5 plus 1 equals 0. You solve for x1 and end up with 13/10. The vector that is the basis for the null space is 13/10, negative 2/5, 1. In this 3x3, the second and third columns are multiples of the first column. This is how we can predict that there will be 2 free variables and that the dimension of the basis for the null space will be 2. You don't have to notice that to do this problem. You start the usual way by row reducing, but if you'd like to first make sure the matrix is dependent, you can start by taking its determinant. Next, to row reduce, you can do 4 times row 1 plus row 2 sent to row 2, and all the components of that row become 0. Then you do 3 times row 1 plus row 3 sent to row 3, and all components of that row also become 0. It is now reduced as much as possible, so you set it up times some vector equal to 0. There is one pivot column and two non-pivot columns, So there are two free variables in the second and third components of the null space vector, and therefore two vectors in the basis for the null space. You start by setting up the vectors. One will have one free variable set to 1 and the other set to 0. The other vector will be swapped. The first component can easily be chosen by inspection, but if you don't prefer inspection, you can set up a simple algebra equation. x1 times -1 plus 2 times 1 plus -3 times 0. Solve for x1 and get 2 as the first component of the first vector. For the second vector, set up -1 times x1 plus 2 times 0 plus -3 times 1 and solve for x1 and get 3 as the first component of the second vector. 2, 1, 0 and 3, 0, 1 is the basis for the null space of this matrix. You can also find the null space of a non-square matrix. This matrix is a 2 by 3 and is dependent. The second column is a multiple of the first column. So I want to start by attempting to put this into upper triangular, by first trying to turn the first component of the second row into a 0. I do this by doing 2 times row 1 minus row 2 sent to row 2, and get 0, 0, 1 as the second row. This is as reduced as I can get this matrix, so I set it up being multiplied by some vector and set it equal to 0. The second column is a non-pivot column, so there's a free variable in the second component of my null space vector, and it's set to 1. I can do the next part simply by inspection, or I can set up a simple algebra problem to see what the first and third component of this vector should be. 0 times x1 plus 0 times the free variable 1 plus 1 times x3 equals 0. I solve for x3 and get 0 as the third component of the vector. Next, to find x1, you can set up x1 times 1 plus 3 times the free variable 1 plus 0 times 4. You solve for x1 and get -3. The basis for the null space of this matrix is one-dimensional. It is the vector -3, 1, 0.